So this is a video, I'm going to call it Notes C. There are no paper Notes C yet. Maybe someday there will be. But this will be videos for connecting the distributive property with factoring. So really we're working toward factoring. So this will be part one of this video. And what we're going to work on is the distributive property and how that connects to factoring out a GCF. And GCF is greatest common factor. So let's do this example. We're going to multiply this out. So this is 3x squared y cubed times x squared minus 3xy minus 2y squared. So we want to multiply that out. Now before we do that, take notice. That's multiplication. Anything in parentheses you see as a single entity. This is all one term. I just think of this as 3x squared y cubed times this. So that's all one term with two factors. Okay, this would be, I would consider that one factor. That would be a monomial. And in parentheses is the other factor, and we would call that a trinomial because there are three terms. Tri for three, nomial just term. So what we see is we see multiplication to several terms. That calls for the distributive property. So I will distribute. And when I do that, all right, 3x squared times x squared. Oh, I'm multiplying the same base, so I add exponents. So notice I need the exponential rules to do this. And times y cubed. Okay. Now 3 times negative 3 minus 9. X squared times x to the first. That's x cubed. Y cubed times y to the first. Remember, you're multiplying the same base, so you add exponents. So that's y to the fourth. And then 3 times negative 2 is minus 6x squared. And then y cubed times y squared, multiplying the same base. It's long distance multiplication, but you are multiplying the same base, add the exponents. This was the answer we were looking for. This is what you get when you multiply this out. And there's this big equal sign, which means these two expressions are equivalent. They say the same thing in different ways, like 4/4 is the same amount of money as $1, but just in a different form. Notice what this answer looks like. The answer has 3 terms in it. We started with 1 term, but when we distributed, we basically split this up into 3 separate terms. And notice every term has a coefficient that's divisible by 3. Oh, wonder why that is. Every term has an x in it. And in fact, every term's got at least an x squared in it. Because if it's got an x cubed, it's got an x squared. If it's got an x to the fourth, it's got an x squared. And notice every term has a y in it. And every term's got at least y to the third. So y to the third here, but if you have a y to the fourth, that means you've got y to the third as well embedded in there. Same here. Okay, so now we're going to quickly reverse this process. Suppose you're asked to factor 3x to the fourth y cubed minus 9x cubed y to the fourth minus 6x squared y to the fifth. Okay, first of all, it's really important. What does it mean to factor? Well, it means you're going to rewrite an expression that starts out, it has several terms, like this one. This one's got 3 terms, into an equivalent expression, so it has to say the same thing, that is all one term, but with several factors. We want to be looking at factors all in one term instead of 3 separate terms. So there are many, many techniques for factoring, but it doesn't matter how many new techniques you learn. Whenever you see this instruction, hey, factor this, the first step in factoring is to factor out the GCF, if there is one. Again, I'm too lazy to write that out. That's greatest common factor, okay? So, doing this, all this is, it reverses the distributive property. It's the best way to think about this. So when you use the distributive property, it's always one term in front of one set of parentheses, and you distribute. So we want to undo that. So to factor out the GCF, you have to find the GCF. Now, there is a GCF if you can see a number that divides into all the coefficients. I see that 3 does. Okay. So I'm going to kind of write this over here. The GCF, 3 is part of that. It's common to every term. Is there a variable common to every term? Well, x is common. And we want as many x's that are common as possible. Well, this has an x to the 4th, but this does not. It doesn't have that many. This has an x squared. This term also has an x squared embedded in there. This term also has an x squared. So x squared is common to all of them. And in terms of the x's, that's the most that it's common. So hence greatest common factor. Notice when you have the same variable, it's always the smaller exponent that goes into the GCF, because this guy's only got x squared. So at most, x squared is common to all 3 terms. Now look at the y's. Yep, the y is common to every term. At most, how many y's show up in every single term? Well, it's not y to the 5th because there aren't 5 y's here. But there's y to the 3rd here, so there are 3 y's here. Hey, there are 3 y's here, and there are 3 y's there. So y to the 3rd is common to all terms. So the GCF is 3x squared y cubed. And remember that we're reversing the distributive property. So the answer should look like, oh, some binomial here times something in a big fat parentheses. Well, the GCF is 3x squared y cubed times something. And what goes here is what I have to figure out. And what I'm trying to get is when I distribute the GCF, I want to be able to get back to these terms here. So one thing I notice, there are 3 terms in my original problem, and look at the signs. There will be 3 terms with these signs inside these parentheses. And then I'll think, 3x squared y cubed times what would give me this term back? Well, 3x squared y cubed times what? Well, 3, oh, we don't need any coefficient there. 3 times 1. X squared times what would give me x to the 4th? Oh, I would need x squared, right? Because x squared times x squared, that would give me the x to the 4th back. Y cubed, oh, that's exactly what I got. Just need the x squared. Okay, minus. Okay, what's supposed to go here? Well, 3x squared y cubed times what would give me this term back? Well, 3 times 3 would give me the 9. I already got the sign right. Okay, x squared times what? How many x's? To get me x cubed, I would need one more x. And then y cubed times what? To get me back up to y to the 4th, I'd need one more y. Then minus, okay, what goes here? All right, 3 times what would give me the 6 back? That'd be 2. And I already fixed the sign, so I'm not worrying about the signs. X squared times what will give me x squared? I don't need to multiply any more x squareds in. Y cubed times what would give me y to the 5th? Oh, I would need y squared. This is factored. And it's actually back to the original problem we started with. Now we're back to all one term with 2 different factors. So y factor. Why do we do this? In fact, why do we even distribute? Well, when you're working with algebra, sometimes, it looks like I dropped a little hump there, sometimes we need factors and sometimes we need terms for our purpose. And I'm going to give you some examples there. And part of the problem when you're first learning factoring, the purpose is it's kind of like not in your face. And then when you see the purpose, it becomes, oh yeah, I need factors here. Oh yeah, I need terms here. But sometimes you need factors, sometimes you need terms. And I'm always thinking, sometimes you feel like a nut, sometimes you don't. So let's try to go over quickly an example of each case. So I think all of you have done some solving of equations, okay? So suppose you want to solve this equation. 3 times 2x plus 1 equals 10. Okay. Well, when you solve, you want to isolate x on one side of the equals. I mean, your goal is to get the term x by itself, and then you have some number on the other side, right? Well, notice what I said, you need to get the term x by itself. Well, x is stuck in the parentheses. I have factors here, and I can't get the x out. But if I distribute, that breaks up the factors into 2 separate terms. And when you're solving, it's actually terms that you add or subtract from both sides. You don't add or subtract factors. So to solve, I need terms. So the distributive property changes these factors into terms. And I'll do the rest of this quickly. You subtract 3 from both sides. Okay. Actually, I think I wanted that to be, 6x, equals 7. And then you divide both sides by 6, and x equals 7, 6. Okay, so there's an example of when you need terms instead of factors. When do you need factors instead of terms? Reducing fractions. You need factors. Okay, for example, if you have 6 times 2 over 2, can you reduce that fraction? Well, let's make sure that you see that the 2 can be thought of as 1 over 2. I mean 1 times 2. 2 can be thought as 1 times 2. So these are factors. They're identical factors, and I can think of this as 2 over 2. What's 2 over 2? Is cancel to 1. This equals 6. So I can cancel identical factors, when reducing. Sorry, my writing is really sloppy tonight. Now, what about 6 plus 2 over 2. Now again, we can see this as 6 plus 2 is 1 times 2. So that 2 can definitely be seen as a factor if you want, but that 2 is a term. Can I cancel these 2's and say that equals 6? Well, you can, but you'd be wrong. We know that 6 plus 2 over 2, remember this acts like parentheses, so get the answer in the numerator first, is 8 over 2, and 8 over 2 is 4. That's the correct answer. It's not 6. You cannot cancel terms. When reducing. So if you want to reduce a fraction, you need factors instead of terms. And let's do one more example. Suppose you're asked to reduce 12x plus 4x squared all over 2x. Okay. Well, these are terms. Do not cancel terms when dividing. I can cancel factors, but I don't have factors. I mean, I can see the numerator as a factor. That's easy enough, but I can't play that trick I can see the denominator as a factor. That's easy enough, but I can't play that trick in the numerator. Those are 2 separate terms. So what could I do? I could factor the numerator. First step in factoring is always look for a GCF. So I'm looking at these 2 terms. Is there a number that divides into both of them for the coefficients? Yep, 4. That's part of the GCF. Is there a variable common to both of them? Yes, an x. What's common to both is just x to the first. So I write the GCF in front of blank parentheses. There are 2 terms here, so I expect 2 terms inside the parentheses. 4x times what would give me the 12x back? That would be a 3. 4x times what would give me 4x squared back? Well, that would be the x. And then over 2x, remember I could think of that as 1. These are now factors. So x over x cancels, and then you can just go 2 goes into 4 twice. So this is 2 times 3 plus x, and you can just leave it that way, leave it in factored form. That's what we'll do in the class. Or you could distribute it if you needed terms for your next step. So whether you leave this answer in factored form or you multiply it out and expand it and get terms, that depends on what you would do with it next. If this was the end of the problem, you're not doing anything, either form is good.